Last week we did proportions. This week we're doing averages, means. It's the only difference, okay? We're also adding a new letter. We've been working with Z a lot. Z, right? Z-scores, Z-score tables, right? The two tables. Well, we're going to learn about a new one, which is, if you look, it's on the back. On the back of your Z-score tables, there's two more tables. We're going to learn about the one to the left. It's called a T table. Okay, not Z. The Z's on the front. So the side with the two normal distributions, symmetrical, those are Z, which we've been using the whole semester. Okay, we're still going to use that one. Not like we're not going to use it. We are going to use that. But we're introducing a new one, which is T. That one has one with normal distribution and one that's skewed. That's how you can know which one's which. The one with the side with two normal distributions at the top, that one's Z. Okay, and it also says Z. You can see on the tables it says Z. Okay, the one on the other side is the first one is we're going to use. The one to the right, we'll use the last chapter. Chapter 11. We'll use that then. Okay, so don't worry about that right now, but we're going to use this guy over here. When do we use it? How do we use it? Well, that's what we're going to go over today. Okay, so first thing. With means. Means is a little tricky because there's two types of intervals for means. There's Z and there's T. How do I know which one to use? Right here. If they give you population standard deviation, if they give you that guy there in the question, in the prompt, you're going to go Z. You're going to go Z. If they don't give you it, you're going to go T. Okay? So when you're reading a problem, once you're done with the problem, you should know if it's a Z or a T. Okay? It's not like something you have to figure out. You just read it. Did they give me the population standard deviation? If yes, then it's a Z. If no, then it's T. I'm going to tell you right now, 98% of the time, it's going to be T. It's going to be T. And I'll tell you why. Because if let's say we have the population standard deviation. Okay. Let's say they tell us what the population standard deviation, and this is an example of a multiple choice question. Let's say they tell us what this number is in the question. What else do we have to know if they give us that number there? What else do we have to know? To get this, I have to know what? The mean, right? The population mean. I have to know this guy as well. Well, here's the problem. The reason I'm doing confidence intervals is to estimate this guy here. So why would I do a confidence interval to estimate a number I already know, right? That doesn't make any sense. It's not logical, right? Why would I do a whole confidence interval, 5 steps, if I'm trying to estimate a number I already know? I already know what the number is, right? That's why we do confidence intervals. It's when we don't have this guy. When we don't have this guy, we try to estimate it based off a sample. Okay? So that's why in real life, neither of these are going to be given. Neither of these are going to be given because why do a confidence interval if you already know what the answer is? Okay? But that's why, like I said, about 98% of the time, it will be a T. T will be the one we use quite a bit. Okay? So it's just, do you know that guy? If you know it, Z. If you don't know it, T. Okay, that's the way, that's the kind of How to know which one is Z, how to know which one to use, Z or T. Okay, so what is T? We've never learned about T. We've been learning about Z since chapter 2. But what is T? Okay, well, T procedures when population standard deviation is non-known. We don't know what it is. When population standard deviation is unknown. So what does this mean for means? Well, it comes from Student's T model. There was a guy, his last name was Student. Okay? Don't ask me why. Don't ask. That's why it's capital S. That's why it's capital S for student, because it's actually a person's name, Student. And they discovered this. They discovered what we're going to talk about here. So they call it Student's T models. Most of the time, we'll just call it T. Okay? I don't really call it Student's T models. I just call it T. So, what happened was these curves have more area in the tails because we are using S to estimate the population standard deviation. There is greater uncertainty and variability. So if we don't know the population standard deviation, we have more variability. So the dashed is normal, Z, right? The dashed is an example of Z. The solid is an example of T with 2 degrees of freedom. I'll explain what degrees of freedom means in a second. And you can see that the dashed has less variability, higher peak, and not as much more area it's got in here, right? We want more or less variability. Well, if we had less variability, the perfect world, in the perfect world, we would use Z every time. But when we don't have the population standard deviation, we have to use it everything based off the sample. So when we do that, we have to use T. Okay? So here's another example. Degrees of freedom. What is degrees of freedom? Degrees of freedom, the formula for degrees of freedom is n minus 1. So let me give you an example of degrees of freedom. So degrees of freedom means every number in the sample has the freedom to be whatever it wants, except for one number. Okay? So let me give you an example. Let me get a separate sheet here. So let's say I know that the mean of a sample is 10. And there are 4 numbers. Three of those numbers can be whatever they want. Big, small, even negative. Decimal, doesn't matter. But the last one has to be a certain number. For example, let's say I put 15 here. I put 20 here. I put 10 here. To be a sample of 10, there's only one answer. There's only one number that can go in there. There's only one number, right? I can't just say, oh, okay, this will be 20. That doesn't make sense because you won't get a mean of 20 or a mean of 10. Okay, you'll get, let's see, 20 plus 10 plus 20. That average is 16.25. That won't work. So I only need to change one number, the last number. So 10 plus 20 plus 10 is 40. To get a sample, to get a mean, to get an average of 10, this would have to be a 0. That's the only number it could be. So we would say the degrees of freedom here, there are 3 degrees of freedom. Because these 3 numbers could be whatever the heck they want to be. They could be anything, high, low. That 15 could be 150. That 20 could be 200, right? But there's one person who has no freedom because it has to be whatever it is to get to the mean. Okay. So that's why we say degrees of freedom is n minus 1, because every number in the sample can be whatever it wants except for the last guy. So degrees of freedom is n minus 1. Okay. How many numbers in the sample can be free to be whatever they want? Right? If there are 4 numbers in the sample, 3 of them can be whatever the heck they want to be. The last guy can't be. It can only be one thing because the mean has to be a certain number. Okay? So the quick way of deciding those is just n minus 1. N minus 1. As degrees of freedom goes up, we get closer. So you see, as degrees of freedom goes from 1 to 2 to 5. So if I have 1 degree of freedom, how big was my sample? 2. If I have 2 degrees of freedom, how big was my sample? 3. If I have 5 degrees of freedom, how big was my sample? 6. And if I have an infinite degrees of freedom, that means my sample size was infinite, right? Perfect world. Perfect world, I have a huge sample, right? The bigger the sample, the better. Well, this won't exist. This is a perfect world. We call that, we have a name for it. It's called Z, right? Up till now, for means, this has no bearing on proportions. Don't get this mixed up with proportions. Proportions, I didn't talk about t, right? Proportions, I did not talk about t. So this does not involve proportions. It only is means. Okay? So yeah, so this is only for proportions. Or sorry, means. It's not for proportions because a lot of students get it mixed up. They look at a proportions question, watch from last week. They'll look at this question here and they'll be like, is it Z or is it T? It's proportions, so it has to be Z. Proportions are always Z. Okay, we didn't talk about that because it's not, proportions is only one. Means is the one that has a choice. Okay, as I get more and more degrees of freedom, less variability, right? Perfect world, it would get to Z, but we don't live in a perfect world, so that's why you will hardly ever see us use Z. Most of the time for means, we use T. Okay. Okay. So here's some red meat for multiple choice. Multiple choice. They love to put these types of questions on multiple choice. These are properties of T. Things about T. First one, we don't know. When we don't know the population standard deviation, that's when we use a sample standard deviation. We use T. Okay. T distribution has fatter tails, is wider than Z distribution. Okay. As degrees of freedom increase, T model starts to look more and more like Z, normal, right? Normal is the Z, right? Perfect world, we'd love Z. So as degrees of freedom goes up and up and up and up, we get closer and closer to Z. We'll never get there, but we get closer there. In fact, the T model with infinite degrees of freedom is exactly normal, right? And we're never going to have infinite degrees of freedom because that means we have an infinite sample. That's not going to happen, right? But the more we have in our sample size, the closer we get to Z. Okay? The main difference between Z and T is that T has more variability. Z is less variable. Okay? All right. So how do we use the t-table? So how do we use the table? Well, I'm going to show you how to use the table right now. So if you have the table in front of you, I'm going to show you how to use that table. It's on the back of the Z table. We haven't used the backside. We're going to start today. Okay? So the first thing you're going to do is you need to figure out degrees of freedom. Degrees of freedom. How do you do that? Well, you find your sample size and subtract 1, n minus 1, right? So if I have a sample size of 20, degrees of freedom is going to be 20 minus 1, which equals 19. I have 19 degrees of freedom. 19 of the numbers in my sample could be whatever they want, but the 20th has to be a certain number to make it correct. Okay. So once you get your degrees of freedom, you're going to go to the column that says DF at the top. So degrees of freedom for this one is 19. So I'm going to go right to the one that says 19. That guy right there. Okay. The next thing is, what type of confidence interval is it? Is it 95? Is it 90? Is it 98? Is it 99? Is it 85? Is it 80? Which type of confidence interval is it? For this one, it's a 95, right? So you're going to go to the bottom, and it says confidence level. We have 95. And then you're going to see where they match. So if I were to go this way for degrees of freedom, I'm on this row here. And if I were to go up in this column for 95% confidence interval, where would they meet? They would meet right at this guy here, 2.093. That's the t-score, not the z-score. That would be the t-score. So we would say this guy has a t-score of 2.093. Now, what is the z for a 95% confidence interval? 1.96. Okay. So 1.96, the number we have is 2.093. T will always be a little bigger, a little farther out than Z because it's got fatter tails. Fatter tails means it's farther out. Okay. Wider tails is the same thing. So T will always be a little bit bigger than Z. Always. Okay. All right, so let's do the next one. Next one is a sample size of 15. Sample size of 15. 15 minus 1 equals 14. 14 degrees of freedom. %99 confidence interval. 99, see 99's right there. So this column the t-score, or the t-critical, I should say, is 2.977. Right? The z-critical for a 99% confidence interval is 2.57. So this one's a little wider. Okay. 26. So let's do 26. 26. That means a degrees of freedom of 25. 90% confidence. 1.708. Normal 95% confidence. Normal, what I mean when I say normal, I mean Z is 1.64. Okay? As my degrees of freedom goes up, I'll get closer and closer to that number. Okay? Let's see, 50. 49 degrees of freedom. We don't have 49 degrees of freedom on our chart, right? Use the closest one. Use the one that's closest. There's a 50, so use that one. It's not exact, but it's the best we can do. For 98% confidence, 2.403. Okay. All right, so I want you to do the rest. I want you to do 5 through 10. Do 5 through 10. There's a couple on the back. What are the T-scores or T-criticals for each of those? Mm-hmm. Yes. Okay, so yeah, 5 and 6 are the same. 5 is the same as number 1. Number 6 we talked about, 1.96. T is always going to be bigger than Z at the same confidence. Doesn't matter how big your sample size is, unless it's an infinite, it's always going to be bigger. Why is that? Because T has more variability. Why is that? Because it's due to we have to rely on only sample data. We have no parameter data to back up on, to fall back on. Everything we can say to estimate is based off the sample. And there's a lot of sampling variability that can happen. Okay? So with more variability comes a bigger, comes a difference. Okay? And then 8, 9, 10, T-scores. Okay? So that's how to use the T. So when do we use it? We use it when we need to use, when we found Z critical, right? Z critical or T critical, right there. That's where we use the table. Those guys right there. Z, if it's Z, we just use the front like we have been. If it's T, we use it just like we have before. This should be T. Okay. It's got 5 parts, same 5 parts. Identify population parameter of interest. This chapter or this section, we're going to have that because we're dealing with means. The true mean, blah, 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 whatever it is. Test statistic, one of these two guys, depending on it's Z or T. Conditions. Remember, first 2 conditions are the same as proportions. The third condition is different. It's not n times p is greater than or equal to 1, n times 1 minus p is greater than or equal to 1 or to 10. It's not those. It's these guys. Central limit theorem, right? Which one of these 3 down here does it apply? Just like you did on the quiz. Okay, just like you guys did on the quiz last week. Okay? Number 1 and number 2 always apply. Means, proportions, doesn't matter. Last one, third one, they're different for proportions than they are means. Okay? But they're no different than chapter 7. The same as chapter 7. And then last one, calculations and conclusion. Conclusion is exactly the same. Where is the conclusion? Where did I put it? Oh, conclusion's a little bit farther down. It's the same sentence frame, just instead of true proportion, you're going to put true mean. Other than that, it's the same as proportions. Okay? All right, so here we go. I want you to do example number 1, A, B, and C. Example number 1, A, B, and C. Determine if the normal large sample condition is met. Which one is the normal large sample condition? Which one is that? The third one. Yep, condition number 3. So it's only asking you to check condition number 3. You don't have to check condition number 1. You don't have to check condition number 2 for these guys. Okay? So do A, B, and C. Okay, so let's see. A, to estimate the average GPA of students at your school, you randomly select 50 students. Here's the histogram. Okay, well, the sample size is 50. So if I go to my options, let's see, it didn't say that the population was normally distributed. Didn't say anything about the population being normally distributed, so I can't use that one. Is my sample size large enough? Yeah, it's large enough. It's bigger than 30. So we would say since n is greater than 30, sample size is large enough by the central limit theorem. Okay. Number 2, how much force does it take to pull wood apart? The STEM plot shows the force in pounds required to pull a piece of Douglas fir apart for each of 20 randomly selected pieces. Okay. So n is 20. So let's go back to our 3 options. It doesn't say anywhere in the question or the prompt that its population is normally distributed. Our sample size isn't big enough. So the last thing we have to do is check the dot plot to see if there's any outliers. Are there any outliers? Well, let's say, how do we know? How do we know if they're outliers? There's an easy way and there's a longer way. How do we know if there's outliers? What's the way to check to see if there's any outliers? No. That's the formula, yeah. That was a long time ago. And you have to calculate numbers. That would be right. It would be a long method, long way though. What's the quicker way of doing that, of seeing if there's any outliers? The calculator has a function. The calculator has a function, a modified box plot, which you can tell if there are. And it turns out there are none. None of these numbers are outliers. Okay? So we have no outliers. Is it skew? Yeah, it's skew. It's skew to the left. Right? So since sample size isn't big enough, there are no outliers present, and we would just say sample data is skewed to the left. That's all we would put. We list our concerns, right? Sample size is not big enough, comma, less than 30. No outliers present. And sample data is skew left. That's it. Just note what you write. Put it in there, right? And then you move on to the next part. Okay, last one, C. Sample size is 20. They don't give us the data. They don't actually give us the 20 numbers. So we have to use the dot plot or the box plot. Are there any outliers there? No. How do we know? There's no dots, right? There's no dots or stars at the end, right? That's how we can tell. So none of those, so no outliers. Is it skew? How do we know if this guy is skew or not skew? Like this guy, it's fairly easy. Just turn your head to the side and see, oh, there's a big clump of numbers over here that are on the high side, right? And not so much on the low side, right? You kind of turn your paper to the side and you can see like, oh, yeah, and then you can draw a shape too. But how do you do that for this guy here?
Since the 600 is the middle of the data and the median is not there, is that how you check?
There's a couple different ways to check. So this guy is skew. We said it was skew to the left. Why was it skew to the left again? Most of the data, a big clump of data, is on the high side, right? Okay. So remember, each of these, represent 25%, right? This is going back to chapter 1. So if there are clumps together, how would that show on a graph? If so, like if there's a clump, right? There's a clump here. How would that show up on a graph like that? Would be smaller. Would be tight. Would be the window here would be smaller, right? This is pretty spread out. That means the numbers are pretty spread out. This means the numbers are pretty spread out. This means the numbers are pretty spread out. All of them are kind of spread out. So there's no real skewness to this. There's real no strong skewness anyway. If this box was like that, I would say there's a very tight window in here. That's because there's a lot of numbers in there, right? Now, where is it? Is it on the low side? Is it on the high side? Just depends. But here there is none. They're all, I mean, this guy, this tail is a little longer, but I mean, not crazy long or not crazy short. So I would say there's really no skewness there. So we would put sample size is not big enough. Right, less than 30. No outliers present, and sample data shows no skewness. I'm not saying it's normal, or I'm not saying it's symmetric. I'm just saying it doesn't really show any skewness, strong skewness anyway. Doesn't really show any of that stuff. And we move on. Okay. Doesn't affect what we do, doesn't affect anything else, doesn't affect calculations, doesn't affect conclusion. We keep going like we normally would. Okay, and then the last one is the confidence interval, the actual conclusion. We always do a conclusion. It's the same. Literally, I cut and pasted that from your last notes. Right? This chapter, you're not going to see proportion, or this section, I should say, it's not going to be proportioned. It's going to be the true mean, whatever it is. Okay. Last section, it was all proportions. This section, it's all means. Okay. That is the difference. Okay. We're not going to have time to finish this example, but at least we can get it started. Okay. So we're going to do a practice problem. Mr. Flores is curious about the mean GPA of students at Central High School. East and West Campus is an old question. Combined. So he decides to take an SRS of 40 students to help him answer that question. The sample mean for the 40 students is 2.98 GPA with a standard deviation of half a grade, 0.54. Use this to construct a 98% confidence interval for the true GPA of students at Central High School. Okay, so before we start, what are the important things that we need? First of all, we have a sample size of 40 students. Next big question, is it Z or is it T? Is this question going to be a Z or is this question going to be a T? But how do we know? No. Do we know? Where is it? Where is it? Where is it? Do we know this guy up here? We do? I don't have that. That's the population. Do I have the standard deviation for all of the students or just for the sample? Just for the sample, right? So if I only have for the sample, it's going to be T. I don't have any data about all the students. I only have data on the 40, right? So it says standard deviation, but that's not population standard deviation. That's sample. So we use S for that, lowercase s for sample standard deviation. Same thing with the GPA. GPA, the reason you don't see averages in there because average is A, GPA, grade point average, right? 2.98. Those are both statistics based off the sample, not parameters. So we're going to use T. It's going to be a T interval. Okay. Step 1, population parameter. True, mean. Well, it's right here. You don't have to say true mean because average is already in there. You could say true mean GPA for students at Central High School. That's what I'm trying to estimate. I'm trying to estimate for everybody, not just those 40. I know for those 40, it's 2.98. But I'm trying to estimate for everybody. What is the true GPA for everybody, not just those 40? Okay. Test statistic or formula. Well, we're going to use, where is it? This guy right here. Since it's T, we're going to use T critical and S. Sometimes it's called S sub X. Sometimes it's just S. It's the same thing. Okay. We'll stop right there. Next thing we're going to do is conditions. We'll do that tomorrow. And then calculations, and then conclusion, and we're done. Okay.